Hello everyone, welcome to my channel Learn Physics with MPG. I am Dr. Mrityunjay Prasad Ghosh, currently working as an assistant professor at SR University, Warangal, Telangana, India. So today we are going to discuss an important topic of basic electronics, that is PN junction diode. So we will discuss the formation of a PN junction diode and its operational principle in forward bias and reverse bias. Further, we will discuss the IV characteristics of a PN junction diode. So let's start the discussion. So in our previous class, we have gone through the types of materials based on their conductivity or resistivity and band structure. So as per the conductivity or resistivity and band structure, materials can be classified into three major categories. So they are conductors, insulators and semiconductors. So conductors have free electrons. So in case of conductors, the conduction band and valence band are overlapped. For insulator, there is a forbidden energy gap in between conduction band and valence band. And the energy of this forbidden energy gap is of the order of 15 electron volt. But in case of semiconducting materials, this forbidden energy gap is less when compared with the insulators. So the forbidden energy gap for semiconductors lies in the range of 1 electron volt to 1.5 electron volt. So further we have discussed about the types of semiconducting materials. So there are two types of semiconducting materials, that is intrinsic semiconductor and extrinsic semiconductor. So intrinsic semiconductor is a pure form of semiconducting material. So this is a extremely pure semiconductors. So it contains no impurity or no doping. But in case of extrinsic semiconductors, so there are certain amount of doping or impurities are present. So there are two types of impurities. One is donor impurities and acceptor impurities, or you can say the trivalent impurities and pentavalent impurities. So if you dope trivalent impurities inside the intrinsic semiconductor or extremely pure semiconductors, then you will get p-type semiconducting materials, where the majority charge carrier is hole and the minority charge carrier is electrons. So if you dope with pentavalent impurities or donut type impurities inside the intrinsic semiconductor or extremely pure semiconductor, then you will get n-type semiconducting materials, where the majority charge carrier is electron and minority charge carrier is hole. So we have discussed all these things in our previous classes. Junction diode. So what is PN junction? Let's start the discussion. A PN junction is an interface or a boundary made of two different types of extrinsic semiconductors, that is p-type semiconductor and n-type semiconductor. So when one side or one half of the extremely pure semiconductor or intrinsic semiconductor is doped with trivalent or acceptor type impurities, and another half or another side is doped with pentavalent or donut type impurities, then a junction is formed, which is known as PN junction. So PN junction can be created by the method of doping. You know about the doping. The doping is a process by which we can add several impurities or different types of impurities into a extremely pure or intrinsic semiconductor. So in general, the fabrication method or fabricating a PN junction diode requires a highly developed semiconducting technology. So there are four methods or four techniques to prepare or to fabricate PN junction diode. So they are grown junction technique, alloy junction technique, epitaxy technique, and diffusion technique. So these are the 4 techniques by which we can fabricate PN junction diode. So as seen in the figure, in a PN junction there are 2 regions. One is N region and another is P region, right? The P region of a PN junction can be represented by acceptor type impurity atoms or acceptor ions and a hole, where the hollow circle represent a hole, right? And the another half or the another side of a PN junction is the N region, which can be represented by donor type impurities atom or donor ions and an electron. The black circle is represented the electrons, right? And the interface separating N region and P region is called metallurgical junction. So this junction is known as a metallurgical junction. So in the P region, the concentration of hole is high, whereas at the N region, the concentration of electron is high, right? So electron from the N region tries to move towards the P region, whereas the hole from the P region tries to move to the N region, because the majority charge carrier for P region is hole and it has high concentration at P region, where the majority charge carrier for N region is electron and it has high concentration at the N region. So electron tries to move from high concentration to low concentration, that is N region to P region, whereas hole also tries to move from P region to N region, because hole has high concentration at the P region, right? So at the junction that is called the metallurgical junction, the electrons and holes are recombined and an electric field is developed at the junction. At initially, the electric field at the junction is not so powerful to prevent the movement of electrons and holes. So as far as more number of electrons and holes are recombined at the metallurgical junction, then a large number of donor ions and acceptor ions are present at the metallurgical junction. These donor ions, that is represented by the positive sign, and the acceptor ions, that is represented by the negative sign. So these donor ions and acceptor ions produce or generate an electric field which is directed from donor ions to the acceptor ions, or the positive ions to the negative ions. As its gain its strength, or as the electric field that is developed at the junction, which is called the metallurgical junction, is high enough, or its gain energy, or it is so powerful at the junction, when large number of electrons and holes are recombined, then it's prevent the further movement of electron and holes at the junction. Then a depletion region is formed at the junction point of a PN junction, right? So a diode is defined as a two-terminal electronic component that only conduct current in one direction. So diode is a unidirectional circuit component or electrical component that can flow current in a unidirectional or in a one direction, right? So this is the circuit symbol of a PN junction diode, right? The triangle indicates the direction of current. Here the triangle that is indicate the direction of current. So current always flow from P side to the N side or from anode to the cathode, right? For the PN junction diode. So in this figure, this is the junction point of a PN junction or P region or N region. This is called the metallurgical junction. So hope you understood. Here there is a two region, that is N region or and P region. The concentration of electron at the N region is high because it is the majority charge carrier for N region. Here the concentration of hole is high at the P region because the majority charge carrier for P region is hole. So hole tries to move from high concentration to the low concentration, that is from P region to N region, whereas the electron tries to move from N region to P region because the concentration of electron is high at the N region. So at the junction point or at the metallurgical junction, the electrons and holes are recombined and leaving behind the donor ions and acceptor ions. So these are immobile donor ions and acceptor ions. So these ions produce a electric field from donor ions towards the acceptor ions or the positive ions to the negative ions. So these ions are immobile. So at the initial stage, the strength of this generated electric field is not so high to prevent the movement of electron and holes. So as long as more number of electrons and holes are recombined, then the number of immobile donor ions and acceptor ions will increase and the strain of this electric field at the metallurgical junction is also increased, right? So when this electric field is powerful enough to prevent the further movement of electron and holes, then a region is formed which is known as a depletion region, right? And this is the circuit symbol of a PN junction diode. So current always flow from P region to the N region or P side to the N side. Here the triangle indicates the direction of current. So this is all about the PN junction. So let's move to the next slide. So now we will discuss the PN junction diode at unbiased condition when no biasing is applied. So no connection, when no external connection are made to the diode, this is called the equilibrium condition. So we now discuss the equilibrium condition or the unbiased condition of a PN junction diode. So as we have discussed that at the P region or the P side, the concentration of hole is high, and at the N region or N side, the concentration of electron is high. So electron tries to move from N region to P region, and the hole tries to move from P region to N region, because the hole tries to move from high concentration to low concentration, that is P region to N region, and the electron also tries to move from high concentration to low concentration, that is from N region to the P region, right? So at junction, electron concentration is much higher in the N side than the P side, right? Here the concentration of electron is higher because the majority charge carrier for N region is electron and the minority charge carrier is hole. Whereas for N region, the majority charge carrier is hole and the minority charge carrier is electron, right? So a diffusion of electron from N region to P region take place, right? So electron moves from the higher concentration to lower concentration, that is the N region to P region, and hole tries to move from p region to n region, right? The diffuse electron recombine with holes. So at the junction, the holes and electrons are recombined and creating negative immobile ions just near the p side. So at the p side, the acceptor ions are immobile acceptor ions are formed, right? But at the n region, immobile donor ions are formed, right? These donor ions and acceptor ions further produce an electric field. We have already discussed these things, right? So this create a electric field which produce electron flow or dip of electron in the opposite direction, right? So as long as or as far as the strain of this generated electric field at the junction is high enough, then it starts to prevent the further movement of electron or hole or the recombination of electrons or holes at the junction, right? And a depletion region is formed, right? We have discussed about these things. So a thin layer is created on each side of the junction, which is developed or which is depleted of mobile charge carrier, right? Known as depletion region or phase charge region. Here, immobile donor ions and acceptor ions are present, and which creates an electric field which prevents further the recombination of electron hole or movement of electron holes from p side to n side or n side to p side, right? It's prevent the movement of hole from p side to n side, and it's also prevent the movement of electron from n side to p side. This region is known as a depletion region or phase charge region. So this is a thin region in the p-n junction diode, right? So I hope it is clear now. So moving to the next slide, we will discuss p-n junction diode, a potential barrier. So we will discuss about the depletion region, which is known as a potential barrier. So due to immobile positive ions on the n side, so this is the donor type ions, right? And immobile negative ions at the p side, that is acceptor type ions, right? There exists an electric field across the junction. So at the junction, an electric field is existed, right? And the potential difference will act as a barrier that restrict the flow of charge carrier, that is electron and hole. So this electric field developed at the junction will prevent the further movement of electrons and holes, right? So this is known as a depletion region, and a potential difference in between the immobile donor ions and immobile acceptor ions at the n side and p side is called the barrier potential or built-in potential for a p-n junction diode. Now, is it clear now? So the built-in potential or the barrier potential depends on these factors, right? This is depends on the type of semiconductor, what type of semiconductor, that is p type, n type, intrinsic, extrinsic semiconductors, right? The type or nature of the semiconductors, or it is heavily doped, the p region is heavily doped or n region is heavily doped. So this is the type of semiconductors, right? It will depends on also the types and concentration of impurity added. So if the p region is heavily doped or lightly doped, where the n region is heavily doped or lightly doped, so it is the concentration of electrons and holes at the n region and p region it depends upon the types and concentration of impurity added to the semiconductor, right? So the barrier potential or the built-in potential depends on the type of semiconductor and type and concentration of the impurity added to the semiconductor. It also depends on the temperature, right? These are the three factors on which the built-in potential or the barrier potential depends for a PN junction, right? So the built-in potential or the barrier potential can be represented or expressed by this equation, right? V naught equal to Vt ln Na dot Nd divided by Ni square, where Vt is the thermal voltage, right, which is equal to 26 millivolt at the room temperature, and Na and Nd are the impurity concentration. The impurity concentration at the donor side and the acceptor side, or the you can say it is the concentration of donor impurity and acceptor impurity, right? So Ni is the intrinsic concentration of charge carrier, right? When there is no doping, then the intrinsic carrier concentration Ni, that is equal to N equal to P. So Ni equal to N equal to P, right? So N equal to P for the intrinsic semiconductor. So this is the intrinsic concentration of charge carrier, right? So the barrier potential at room temperature for silicon, or the built-in potential at room temperature for silicon, is 0.7 volt, and for germanium it is 0.3 volt, right? Hope it is clear now. So now moving to the next slide. So now we will discuss the biasing of PN junction diode, right? So the process of applying external voltage to a device is called biasing. So what is biasing? So the process of applying external voltage to a device. So here PN junction is a device, PN junction diode is a device. So the process of applying external voltage to a PN junction diode is called the PN junction diode biasing, right? So the external voltage can be applied by two methods, right? One is forward bias, another is reverse bias. So what is forward bias? Either if the positive pole of the battery is connected to the P side of the PN junction diode, then it is called the forward bias condition, right? Or you can say the PN junction diode is in forward bias. If the negative pole of the battery is connected to the P side or anode, and the positive pole of the battery is connected to the cathode or the N side, then it is in reverse bias condition. So you can say that the PN junction is in reverse bias condition. This is P, this is N. If the N side is connected to the positive pole of the battery and the P side is connected to the negative pole of the battery, then it is called the reverse bias condition, right? Did you get it? So anode or the P region is connected to the positive terminal of the voltage source, and the cathode is connected to the negative terminal, then it is called the forward biasing, right? For reverse bias, the P side or the anode is connected to the negative terminal of the voltage source or battery, and the cathode, that is the N region, is connected to the positive pole or the positive terminal of the voltage source or the battery, is known the reverse biasing condition, right? So there are two methods for biasing the PN junction diode. One is forward biasing, another is reverse biasing. What is biasing? Biasing is basically a process of applying external voltage to a device. So this is called the biasing, right? So there are two types of biasing you can apply for PN junction diode, that is forward biasing and reverse biasing. In forward biasing, the P terminal or the anode of a PN junction diode is connected to the positive terminal of voltage source or battery, and the N side or N region or the cathode is connected to the negative side of a battery or voltage source, then it is called the forward biasing. In case of reverse biasing, if the P side of a PN junction diode is connected to the negative pole of a battery or voltage source, and the N side or N region or the cathode is connected to the positive pole or the positive terminal of a voltage source or a battery, then it is called a reverse biasing for the PN junction diode. Hope it is clear now. Now moving to the next slide. So we will discuss the IV characteristics of PN junction diode in forward condition, in forward bias condition and reverse bias condition, right? So when the positive terminal of a battery is connected to the P region or the P side of a PN junction diode, and the negative terminal is connected to the N region of a PN junction diode, then it is called a forward biasing, right? So large number of electron. So when a PN junction diode is connected or a forward biasing is applied to a PN junction diode, then a large number of electrons from the N side are drawn to the positive terminal, right? Here the majority charge carrier at the P region, that is hole, which tries to move to the N region, right? When you applied positive pole of the battery to the P region and the negative pole of the battery to the N region. That is in forward bias condition or forward biasing condition, the electrons from N region tries to move P region, whereas the holes at the P region tries to move at the N region, right? So as a result, the width of the depletion region decrease. You can see in the figure, the width in forward bias condition, the width of the depletion region decrease, right? So as the forward voltage is increased, then the barrier potential is progressively reduced to zero or negligible, right? So the barrier potential that is produced by the depletion region, so width of the depletion region is decreased, and the voltage or the potential barrier that is created at the junction at the depletion region will reduce, right, at the forward biasing condition. Okay, so if you see closely the IV characteristic, so after a certain voltage, that is known as a barrier potential or knee voltage, the current start to increase sharply at the forward bias condition, right? Did you get it? So here at forward biasing condition, the hole converts negative ions into the neutral atom, right? And electron converts the positive ions into the neutral atoms, right? And the width of the depletion region will reduce, and hence the barrier potential is also reduced, right? And if the barrier potential or the depletion region reduce, then it's allowed more majority carrier to flow across the junction. Majority carriers for electrons for N region is electron, and the majority carrier for P region is holes. So they allow, if the width of the depletion region decrease, then it's allow more majority carriers to flow across the junction, right? And beyond a certain point, that is the knee voltage or the barrier potential, the current increases almost linearly with the increase of forward bias voltage. So after a certain voltage, that is known as a knee voltage or the barrier potential, the current increase almost linear with the increase of this forward biasing voltage. So this is the characteristic or IV characteristic of a PN junction diode in forward bias condition, right? If forward voltage is increased beyond a certain value, extremely large current will flow and PN junction may destroy due to the overheating. So if you increase the forward bias voltage beyond a certain limit, then extremely large current will flow and which may destroy the PN junction due to the overheating effect, right? So this is the characteristic of PN junction when forward bias is applied to it, or it is called the IV characteristic of PN junction diode in forward bias condition. So moving to the next slide. So now we will discuss the characteristic or the IV characteristic of PN junction diode in reverse bias, right? So reverse bias means the P side of a PN junction diode is connected to the negative terminal of a battery and the N side of a PN junction diode is connected to the positive pole of the battery. Then it is called the reverse bias, right? So in reverse bias, large number of electrons in the N side are drawn to the negative terminal and the hole in the P type materials or the P side are drawn to the positive pole of the battery, right? Here the majority charge carrier is hole. So hole tries to move or it is attracted by the negative pole of the battery, where the majority charge carrier for the N region is electron, which is attracted by the positive pole of the battery. So as a result, the width of the depletion region will increase, right? So as the reverse voltage is increased, then the potential barrier or width of the depletion region is increased, which resulting in a very high junction resistance. So as the depletion region will increase, if we apply the reverse bias to a PN junction diode, then the resistance at the junction will become very high, right? So there is no possibility of majority charge carrier to flow from N region to P region or P region to N region, right? Because the resistance of the junction is high and as the width of the depletion region is increased at the reverse bias condition. Did you get it? But you know that there is a minority charge carrier for P side or the P region. The majority charge carrier is hole, but the minority charge carrier is electron. So some amount of electrons are present at the P region. Whereas for N region, the majority charge carrier is electron, but the minority charge carrier is hole. Right? So some amount of hole are present at the N region. So you will get some current due to the movement of minority charge carrier, right? So minority charge carrier generates a small amount of current, right? Because it can cross the junction and which leads to a small amount of current which is known as a reverse saturation current, right? Which is in the range of microampere. The forward bias current for a PN junction diode is in milliampere region or domain, whereas the reverse saturation current in reverse bias condition is in microampere region, right? So on increasing of reverse voltage, there is a certain point which is known as a breakdown point or the breakdown voltage at which the reverse current increase sharply or suddenly. After breakdown voltage, the reverse current increase sharply, right? This voltage is known as a breakdown voltage. So this is the IV characteristic of PN junction diode at reverse bias condition. Did you get it? So this is the complete IV characteristic of a PN junction diode. So this part is for forward bias and this part is for reverse bias. Here, after a certain voltage known as a knee voltage or the barrier potential, that is 0.7 for silicon, 0.7 volt for silicon and 0.3 volt for germanium. After this voltage, the forward bias current increase sharply, right? For reverse bias, this is known as a reverse saturation current. So there is a voltage which is known as a breakdown voltage. After that, the current increase sharply, right? So if you increase forward bias, then if you increase the forward bias voltage very high, then after a certain point, the PN junction will destroy due to overheating. Similarly, in reverse bias condition, if you increase the reverse bias voltage after a certain point, that is the reverse breakdown voltage or the breakdown voltage, then current will increase sharply, right? So there are two types of breakdown. You know what are they? One is Jenner breakdown, another is avalanche breakdown for PN junction diode, right? You know about the Jenner diode. Jenner diode is a special type of PN junction diode which is designed to operate at the breakdown region, right? So there are two types of breakdown. One is avalanche breakdown, another is Jenner breakdown. Okay, so this is the IV characteristic of PN junction diode. This curve is for forward bias condition and this curve is for reverse bias condition of a PN junction diode. Total, it is called the IV characteristic of a PN junction diode. Did you get it? So this is the equation, current equation for a PN junction diode, right? This equation is also known as a Shockley diode current equation, which is ID equal to Is e to the power Vd eta Vt minus 1, right? Where ID is the current through the diode, Vd is the diode voltage, okay? Is is the leakage current or the reverse saturation current at reverse bias condition. Eta is called the ideality factor, which is 2 for the silicon and 1 for the germanium. So it's depend on the material property. Okay. So for silicon, the value of eta is 2 and for germanium it is 1, right? Vt is called the terminal voltage. So which is equal to kVt by Q. And the terminal voltage at room temperature is nearly equal to 26 milli electron volt, right? Other terms, you know, this is the Boltzmann constant, this is the temperature in Kelvin, and this is the electronic charge 1.6 into 10 to the power minus 19 coulomb, right? So Vt thermal voltage can be expressed as kBt, that is the Boltzmann constant. Kb, T is the absolute temperature or the temperature in Kelvin divided by electronic charge or charge of the electron, which is equal to 1.6 into 10 to the power minus 19. So this is the current equation or Shockley diode current equation for a PN junction diode, right? Did you get it? So what are the properties of this equation? So when no voltage is applied or the applied voltage is 0, then you will get no current, right? So no current flow through the diode. So when Vd equal to 0, so e to the power 0 equal to 1, so you will get no current. Okay, so if you don't apply, if you do not apply the voltage to the PN junction diode, you will get no current as per the Shockley current equation for PN junction diode. When the applied voltage is positive, this means at the forward bias condition, the current increases exponentially, right? Because e to the power V by eta Vt very greater than 1, right? So at reverse bias, the current increase exponentially, right? Because this term is very small for reverse bias. Then you will get IR is equal to minus IS. What is IS? IS is the reverse saturation current or leakage current. So this is the characteristic of, this is the IV characteristic of a PN junction diode. Did you get it? So in this lecture we have discussed about the formation of PN junction diode. We have also discussed its biasing condition, that is forward biasing and reverse biasing. We have also discussed the depletion region, the potential barrier. We have also discussed the forward bias and reverse bias condition for PN junction diode. We have also discussed the IV characteristic of a PN junction diode, right? Hope it is clear now. So thank you for your patience.